Thank you. Can you hear me? Yes. So first of all, let me thank the organizers and Alessandro in particular for putting together this very nice meeting and inviting me to speak. So this is the title of my talk, and so in order to try to fulfill the spirit of a vision talk, I decided to start with some very general motivations, so it will not be immediately clear what my title is about. So how does it work, the pointer? Maybe. But OK, hopefully it will become clear as we go. So my seminar is about an approach to quantum field theory. So let's start from there. So quantum field theory is our framework that puts together quantum mechanics and locality. And as we all know, it's very successful. And we know that it's very successful because we have a very well understood method to obtain predictions, which is the use of perturbation theory. And this relies, of course, on the existence of some small coupling constant that we use to expand observables. However, I mean, even though in some cases we know how to do this, it's fair to say that in general it's still an open problem to understand how to compute observables in the regime of strong coupling, where our interaction strength is of order 1. And this is not something that it's easy to avoid. One reason to understand this is from the point of view of the renormalization group flow, of which I drew a cartoon here. So even though we might start with some microscopic description at small scales, which is weakly coupled, one thing that we learn in quantum field theory is that the coupling constant in general is a function of the length scale. And so as we increase our length scale, we might go to the regime of strong coupling. And so in this framework, the question becomes, if I give you some microscopic description, how are you going to go about computing predictions for the macroscopic observables? So in particular, a question that one encounters often is very hard to answer is, if I give you some microscopic description, can you tell me if there is going to be a mass gap above the ground state? So that's a very hard question. And OK, so this is the case of massive quantum field theory. But then there is a special case, which is a little bit more tame, which is the case of conformal field theories. So conformal field theories are a special case of QFT in which we don't have any mass scale, and so we have a larger symmetry group. They are useful, for instance, to describe the limiting case of mass in quantum field theory, so in the limit of very small or very large scales. So they are sometimes called signposts in the space of quantum field theory. And in this case, it's sometimes possible to make progress even at strong coupling, using only consistency conditions and symmetry. And this is what has happened in the last 15 years, for instance, in the program of the conformal bootstrap. So a very natural thing that one might hope is, OK, can we build on this progress to somehow also use it for massive quantum field theories? Of course, there is not a single way to try to do this. One way one might try is, for instance, to use this picture. If we know how to solve the theories that live at this signpost, then we can try to deform. But that's not what I want to do, what I want to talk about today. So another possibility, the one I will talk about, is to use anti-de Sitter space as a background for quantum field theory. So I want to argue that somehow it's a bridge between the two worlds of massive and conformal quantum field theories. OK, so this is the metric of idea space, Euclidean, and the cartoon on the right. And as we know, this is a maximally symmetric space with negative curvature. And the symmetry of this background is the same as the conformal group in one lower dimension, as we all very familiar with from ADS-CFT. If we study a quantum field theory in this background, then we can ask what is the analog of scattering amplitudes. And the analog of scattering amplitudes are correlation functions of local operators that are inserted at boundary points. Okay, so I'm free to study this subset of observables. And this is a very rich subset of observables because it satisfies the conformal symmetry thanks to the symmetry of the background. And so what we discover is that in any massive quantum field theory, once we place it on this background, we have a very rich subsector which forms a conformal field theory living on the boundary. So that's the kind of connection that we talk about today. So summarizing this introduction, this seminar is about studying quantum field theory, rigid quantum field theory in an anti-de Sitter background. And let me list, besides what I already said, some reasons why I think this is nice. So we saw at the beginning that one of the problems in studying quantum field theory is that sometimes we have very large fluctuations at large distances, which make the theory hard. And ADS also behaves, in a sense, like a box. So it provides us with some IR regulator. It is an IR regulator which has a lot of symmetries. So in that sense, it's much better than putting your quantum field theory in a box. And so another nice thing of having a radius is that you can use it to probe the theory at different scales. And on the other hand, okay, so far, I mean, an IR regulator with symmetries could also be a sphere. I could put my theory on a sphere. But there are a few points why ADS, I think, is better than a sphere. So first of all, it has an infinite volume. Even though it has this property of being like a box, actually the volume is infinite. So this means that you don't have to give up on many interesting field theory phenomena, such as symmetry breaking or phase transitions. And what I said already in the previous slide, unlike a sphere, we have this very rich set of asymptotic observables, which are the correlation functions of local operators inserted on the boundary, which form this boundary conformal field theory. Okay, so this is the setup, the general setup. Now let me try to go towards my title. So let's specify a little bit and say what we want to do. So the setup that I want to consider in this general framework is the case of dimensional transmutation for a field theory in anti-de Sitter. So I want to consider the case in which our microscopic description is some UV classical theory which has massless degrees of freedom that are weakly interacting. Okay? And then, as it often happens, however, in the IR, the theory develops a mass gap. So schematically here I wrote it in the form of a dynamically generated scale. And so if we now vary the radius of ADS, so it's like varying the size of our box, we can interpolate between these two regimes. Okay? So we have massless degrees of freedom when ADS is small, and then we should see this mass gap when ADS is large. And at least in some cases, one can argue that actually there should be a sharp transition between these two regimes, which, as a result, should be detectable from the point of view of the CFT living on the boundary. So this gives us what I think is a very nice opportunity, which is the opportunity of studying the boundary conformal field theory as a way to detect, or perhaps optimistically even try to prove the existence of the mass gap in the bulk. Okay, so that's the goal. So now that's the outline of the more technical rest of my talk. So first, I will give a brief review of the example that inspires this story, which is the example of Young-Mills in four-dimensional anti-de Sitter space that was studied in this very nice paper some 10 years ago, or a bit more. And then I will mention my work in which, with Christian Copetti, Zimiji, Shotakomatsu, in which we studied two-dimensional examples, so simpler toy models of this. In particular, we looked at ON sigma models and ON Grossneve model. Okay? And in this setup, what we could use is an additional computational handle, which is the large N expansion. And OK, it's worth mentioning that all the foundational papers on large N expansion in quantum field theory came out 50 years ago, so we should celebrate. And so let me start now with the Young-Mills in ADS4. So again, what we're going to do is that we're going to vary the size of our ADS, which here I depicted as the disk. And as we cross the scale set by the dynamically generated scale, we are going to argue that there is a transition. So let's start here on this end. So on this end, perturbation theory is reliable. And so we can reliably look at our Lagrangian and decide what to do. So if you look at our Lagrangian, one thing that we can do is that we can impose Dirichlet boundary conditions on the gauge fields, meaning that we take our non-abelian gauge field and we say that it behaves in a certain way near the boundary. And in particular, it defines this operator J mu A, which from the equation of motion, we see that it's a conserved current. Okay? So far, this is a very usual story to anybody who studied ADS-CFT. I'm just saying that with this boundary condition, a bulk gauge symmetry gives a global symmetry on the boundary. On the other hand, we think we also know something about what happens when ADS is very large, right? Because ADS is very large means that we're basically in flat space. So when we are in flat space, we expect that there should be no colored asymptotic state, and there should be a mass gap, right? So the mass gap, once we are in ADS, talks to the dimensions of operators that we see in this boundary CFT. So all the dimensions should scale like the length of the ADS if we have a mass gap. So in particular, all the dimensions of boundary operators should be much greater than 1 in this limit. In particular, this current, so if a conserved current doesn't have a parametrically large dimension, it has protected dimension. So somehow, in this limit, this current must have disappeared. And we can argue precisely that this should be a sharp transition. It cannot be a continuous change. And the reason why it should be a sharp transition is because when we are in the perturbative regime, we can check. So what is the perturbative regime? It's just a mean field theory, sometimes also called generalized free theory of this operator, which is a current. And then we have small corrections to it. And you see, there is no candidate operator we can build here that can possibly appear on the right-hand side of the conservation equation. Because you see, if an operator appears here, it must have dimension 3 and be a scalar operator in the adjoint representation, and just there is no candidate in the free theory. So since there is no candidate, there must be a continuous range of L such that the theory keeps having the conserved current, okay? And so there should be a sharp transition at some critical length, which we expect to be of order of the dynamically generated scale, okay? Now, what are the possibilities for these transitions? One can imagine various scenarios. So one possibility is that perhaps there is some bulk charged scalar that condenses. So in each of these, we can have both the point of view of the bulk or the point of view what we would see from the boundary CFT. So in the boundary CFT, this would mean that there is some adjoint scalar operator which becomes like hits dimension 3 and then recombines with the current. So it can appear. Now we have something that can appear on the right-hand side, and so this makes our current lift from the spectrum. Another possibility is that somehow the gluon states decouple at some point. So this would mean that from the point of view of the boundary CFT, you see the two-point function of the current is what controls the norm of the gluon state. And so it could be that this coefficient Cj, which is a boundary CFT observable, perhaps continuously go to 0 at some critical value, and then the gluons disappear. That's another possibility. Or another thing we can imagine is that maybe the the boundary condition becomes unstable because there is some weakly coupled scalar that somehow emerges from the as a bound state of gluons, and this weakly coupled scalar gets a mass which is below the Bertalanffy bound. Okay, so that's another possibility, and it has also some explanation from the point of view of the BCFT. Let me not get into that. Now, what we did in our work is that we looked at these 2D toy models, and motivated by what happens in these 2D toy models, we actually proposed a generalization of this scenario 3, because you see, one little shortcoming of this scenario 3 is that somehow, in order to be talking about a scalar that goes below the Bertalanffy bound, I need to rely on some weak coupling intuition, right? Because I have this scalar that has negative mass squared. But this can be phrased more generally, without relying on any weak coupling idea, by saying that what we call marginality. So it could be that at some point, a singlet scalar operator hits dimension 3, okay? So what happens in this case is that you see this is a singlet, so you're forced, when it becomes marginal, you're forced to add it to your Lagrangian, and you should ask yourself the question, what is the beta function of this guy, okay? And you can prove in general that if on one side, let's say, you could satisfy the constraint that the beta function of this coupling is 0, and you found that you have a allowed conformal boundary condition, then as you increase the coupling past the point where delta became 3, actually you cannot satisfy anymore the beta function, okay? You cannot satisfy anymore the beta function, and okay, this is can be described in the language of merger and annihilation. So the boundary condition that you had before disappears. Okay, so this is what I think is the most likely scenario. So I think this is a nice story, and perhaps suggests that one could try to set up a bootstrap approach to the mass gap in Young-Mills. So what we described is that once we put Young-Mills in ADS4, automatically we get a family of CFT trees. So non-local just means that since I don't have gravity in the bulk, then the CFT trees don't have a stress tensor. But for the rest, they are exactly the same as any CFT. That have a global symmetry, which is exactly the gauge group. And then this continuous family is parameterized. For instance, you can parameterize it using the value of Cj, which is in correspondence with the bulk coupling at the ADS scale. And then we know that when Cj is very large, we approach the mean field theory. We can compute perturbation theory, for instance, and some people already obtained some of the CFT data at order 1 over Cj. But the goal is really to try to go beyond perturbation theory and try to see that at some point this boundary condition must disappear, okay? So can we somehow prove that this boundary condition, the Dirichlet boundary condition, cannot exist at arbitrarily small Cj? That would be, I think, like a long way towards, in a sense, proving the existence of the mass gap in Young-Mills. Probably to not be accepted by the Clay Mathematical Institute, but still. So now, in the case of ADS4, this transition that we described is a confinement transition. So now I told you that what motivated me to look at this marginality condition were actually 2D examples, which I will now plan to discuss. So first I need to tell you what is an analog of this confinement-deconfinement transition in the case of ADS2. How am I doing with time? 7 minutes. Okay. So the analogous phenomenon that we studied is what could be called a Goldstone gap transition. So what we did is we considered bulk theories which have a continuous global symmetry. So this time the global symmetry is in the bulk, okay? And when I am in the regime of perturbation theory, I can impose a boundary condition that breaks this symmetry. So this is just a boundary condition in which the normal component of the current is not 0 at the boundary. And this operator Ta which appears as the normal component of the current at the boundary, it's actually protected in the boundary CFT. It's always of the same dimension as the boundary dimension. So it's a marginal operator. So what happens is that every time you impose this boundary condition, you actually have a continuous family of boundary CFTs. It's kind of an analog in ADS of the Goldstone theorem, right? This family of CFTs, you should think about it as the same as having a manifold of vacua parameterized by your Goldstone boson. So this boundary condition is like spontaneously breaking a symmetry in ADS. On the other hand, if we are in two dimensions, we know that when L is large, Goldstone boson should not be there. So again, there should be a transition in between. So the objective, what we did in our paper is that we try to understand very well this transition in two-dimensional examples that are under control thanks to large N. And OK, so now I will not give a lot of details, but we did this, for instance, for the ON model in ADS. And this is the model of just n scalar fields with a constraint. And at large N, the usual trick to solve it is to introduce this Hubbard-Straton of each auxiliary field. So the first thing you do is that you expand around some VEV, and you look for the gap equations, for the vacuum equations. And OK, let me go fast over this. Like, the surprise is that in flat space, of course, you find that there is no symmetry breaking in two dimensions. Well, in ADS, you find that there is a regime of lengths when length is sufficiently small for which symmetry breaking can happen. So this is the picture. So you have the length of ADS. When length is small, you have symmetry breaking. And then for large length, you have a gapped phase. And then, OK, so far I just told you that you do this analysis of the bulk gap equations. So now you can ask me, how do you see this transition from the point of view of the boundary CFT? So that's what we set up to answer. And in order to do that, we just looked at the spectrum of, so we started from this phase, which is very well understood because it's weakly coupled. We just have our Goldstone bosons. And then we looked at the spectrum of ON-1 singlet operators. And what we observed is that as we go towards the transition, one of the operators hits marginality. A singlet operator hits marginality, and that's what destabilizes in the way I described before. So there is a merger and annihilation. OK, let me skip this. This is the details of how we computed the spectrum. But this is the picture, you see. We have these black lines are the spectrum of operators in this weakly coupled boundary condition with symmetry breaking. So what you see is that as you increase L, at some point, the lowest operator hits dimension 1. And that's precisely when so the boundary condition disappears, and you flow, and you're forced to go to the new boundary condition. It turns out that the correct boundary condition you end up in is still a Dirichlet kind of boundary condition, but which preserves the ON symmetry. I guess now. 3 minutes. OK. So yeah, that's the picture. At this transition point, an operator becomes marginal. And if we try to push the symmetry breaking boundary condition further, you actually discover that it becomes complex. Some observable in the spectrum become complex, so it's not acceptable anymore as a unitary conformal boundary condition. And so this is the picture that, like our manifold of vacua, continuously shrinks, and then we flow to the symmetry preserving phase. But the important point is that we managed to detect this from the point of view of the boundary CFT. Okay? So we have a condition which is purely in terms of boundary CFT. OK, so let me summarize. So I discussed transitions from gapless to gapped phases in ADS. And the focus of my work has been on solvable examples in 2D, which point towards, so what we gain from them is that they point towards one particular mechanism for the disappearance of the gapless phases, which is the mechanism of merger and annihilation. And I think there are several interesting future directions. So one clear thing to do, it was already mentioned in previous seminars that 1D CFTs are supposed to be easy. So one thing we should try to do is to try to actually bootstrap the boundary conditions for these ON sigma models and also for Gros-Neve. I didn't have time to discuss Gros-Neve, but the story is very similar. And actually using numerical conformal bootstrap, I would like to try to actually prove this transition to the gapped phase even at small n. I think there is still a role to be played by solvable examples in this context to gain more intuition about what happens. And one solvable example that doesn't rely on large n, but instead relies on supersymmetry that I'm looking at is the one of n equals to super Yang-Mills in ADS4. Also there should be a transition between non-abelian Coulomb phase when ADS is small to some Coulomb phase when ADS becomes large. A bit of a mystery is, I told you that there is this merger of annihilation, but there is a mystery of what is this Dirichlet prime, we might call it, boundary condition that merges with the Dirichlet boundary condition in Yang-Mills and makes it disappear. So for instance, one definite question is whether this boundary condition also exists in the regime of weak coupling or whether it comes in some weird trajectory from strong coupling. This we don't know. And also a very concrete thing that I'm also looking at with some students and collaborators is that we definitely should compute more perturbative data for Yang-Mills in ADS4. Okay, thank you.
Thank you very much, Lorenzo. Are there any questions?
Thanks for the nice talk. So something that is not clear to me is that, okay, you start with Yang-Mills in ADS, and then you say, okay, there is a BCFT describing that. But is it obvious that this would-be CFT satisfies all the axioms of, all the bootstrap axioms of CFT?
Well, I think the only thing that it doesn't satisfy is the existence of the stress tensor, as I mentioned. But for the rest, yes, I mean, you can build all the charges acting on local operators, and the boundary correlation functions will satisfy crossing symmetry. So,
okay, they do satisfy crossing symmetry. But
well, maybe one thing that you have in mind is that sometimes you might want to define local operator insertion with some lines attached. But here I'm talking about genuine local operators on the boundary. The infinitely many of them must exist, and they satisfy the usual axioms of correlation functions in a conformal field theory.
But if you do, for example, block decompositions, maybe you see more operators than what you would want to. I don't know.
There exists a convergent boundary operator product expansion. It's very similar to the case of boundary CFT in that sense. Of course, what you don't have is the bulk OPE, if the theory is massive in the bulk. But you can easily prove that there is a convergent boundary operator product expansion, which is like the boundary operators appear there, and you can build them in this way, like pushing bulk operators close to the boundary. You create some. You can see what is the spectrum of boundary operators.
Okay, thank you.
No problem.
All right. Yes.
So I suppose that Coleman-Merman-Wagner theorem doesn't apply to ADS2.
Exactly, it doesn't. So that's exactly the point that, you see, we have a full range of lengths in which there is spontaneous symmetry breaking. But of course, at some point, Coleman-Mermin-Wagner must kick in. And so this is precisely this transition, that when you try to make ADS large, at some point you must have a transition towards the gapped phase.
So the infrared divergence is therefore not that severe as in flat space?
Exactly, exactly. So this, you can see it from the effective potential, if you want, when you study the gap equation. You see, when you do the gap equation in flat space, the behavior when the Bebo-Debar-Satronovich field is small is this divergence. So this divergence is responsible for the fact that you don't have spontaneous symmetry breaking solutions. But if you do it in ADS, the log of sigma gets replaced by a log of L, and so you have spontaneous symmetry breaking solutions.
So what you would expect at finite n, like in the or 10?
Yeah, I mean, it's not like I have a lot to support my belief, but I do think that something similar should work also at finite n. And I think there is a strategy to do this, which is to do bootstrapping the conformal field theory on the boundary. This can be done also for small n.
So imagine if I would start doing calculation in your theory for small radius of ds. So you get some perturbative expansion, you sum it, you have this coupling constant running, you have dominical scale appearing. On the other hand side, you're going to have some non-perturbative corrections also.
Yes.
Appearing. Those non-perturbative corrections will have dependence on n. Do I understand correctly that in large n limits, they will be dying?
You're saying that I might be worried that at large n I suppress some non-perturbative corrections?
Yes.
And then the picture might be dramatically different at small n.
One thing which will change, which I'm certain about, that your argument about phase transition was based on the collision of two different operators.
Yes.
And this collision will never happen for finite n. The fact that you have a collision is an artifact of going to large n limit.
No, but sorry, the collision was not, perhaps you have in mind that I have two operators of different dimension that become of the same dimension. No, that's not what I meant. What I meant is that one operator, just one, becomes marginal. So one operator hits dimension, which is the same as the dimension of space-time. That can happen, right? I'm not saying that two levels match, cross. I'm just saying that one operator becomes marginal. So that happens all the time, even in finite time CFTs. And if this happens, then you have an argument that the beta function for this guy cannot be satisfied on the other side. So that's why there is a merger and annihilation, but there are two CFTs that merge, not two energy levels.
But this picture which you had at the very end, you have these different branches of these functions. One.
You mean this one?
This one.
Right, but you see...
I'm talking about upper one, yeah.
Yeah. But this happens... OK, so maybe the continuity here is a bit strange, the continuity of the transition. But you see, precisely from the fact that this picture is continuous, you see, the manifold of vacua shrinks to 0 size, and then you start getting a mass. So there is a transition, but it's a continuous one. So it must somehow happen that this second operator must become some other operator after the CFT stops existing.
I'm claiming, if you go to large, this happens because you went to large unlimit.
Okay.
If you include one corrections, you will never have this happening.
Okay, so it could be that what you're saying, I think, is that this continuity here will not happen anymore. Okay, that's possible.
All right. I think in view of time, maybe we can postpone further questions to further discussions. And let's thank Lorenzo again for the nice talk.